Now let's return to the study of magnetic field after discussing what is an electric current. We have seen the connection between magnetism and electricity from the experimental results obtained by Ørsted. So, in this part, we employ the methodology of analogy to study magnetism. An electric field is produced by a charged object, which is represented by the symbol E. Also, we have a magnetic field around a magnet. Historically, we have used the symbol B to represent a magnetic field. The direction of the magnetic field B at some point is the direction in which a compass needle points at that location. Just like the electric field, we also could visualize the magnetic field by drawing field lines. Please look at this figure. We put some compass needles around a bar magnet. The compass needles line up under the action of the magnetic field produced by the magnet. Thus, we could draw the magnetic field lines of the magnet by following these needles. Notice that the magnetic field lines outside the magnet point away from the North Pole and toward the South Pole. Here, we use iron filings to show the patterns of the magnetic field lines. The direction of the field is the direction a North Pole points. Please look at these figures. This is the field lines due to unlike poles. We could find it's similar to the pattern of the electric field lines produced by an electric dipole. On the other hand, the field lines produced by the like poles is similar to the electric field lines created by the charges of the same sign. Now please recall how to define the electric field. We put a test charge in the electric field. The test charge could experience a force exerted by the field. Then we define the electric field as the electric force on the test charge divided by the charge. That means the field is the electric force on the unit positive charge. Similarly, we could quantify the magnetic field B at some point in terms of the magnetic force Fb acting on the test charge placed at that point. We place a point charge Q in the magnetic field and examine the force acting on the charge in terms of both the magnitude and the direction. It's found that some experimental results are similar to those for experiments for electric force. Some are totally different. Now, let's examine the magnitude of the magnetic force on the particle of charge Q. First, the magnitude of magnetic force Fb is proportional to the charge Q of the particle. Second, Fb is proportional to the magnitude of the magnetic field vector B. Third, Fb is proportional to the speed v of the particle. Fourth, if the velocity vector makes angle theta with the magnetic field, Fb is proportional to sine theta. When a charged particle moves parallel to the magnetic field vector, Fb acting on the particle is 0. Then, how about the direction? From the experiment, we found that Fb on the negative charge is directed opposite to the force on the positive charge moving in the same direction. And also, Fb acts in a direction perpendicular to both V and B. That is, the magnetic force is perpendicular to the plane formed by V and B. These results show that the magnetic force on the particle is more complicated than the electric force. The magnetic force depends on the velocity of the particle and its direction is perpendicular to both V and B. The figure here is showing the details of the direction of the magnetic force on the charged particle. Based on these experimental results, we could summarize the relationships of Fb, V, and B, which is expressed by this vector equation. FB equals QV cross B. From the vector equation, the magnitude of the magnetic force on the charged particle is QVB sine theta, where theta is the angle between V and B. From this expression, we see that FB is 0 if V is parallel or antiparallel to B and reaches maximum value when V is perpendicular to B. Therefore, the magnitude of the magnetic field B can be determined by this one. B equals maximum FB divided by QV, which is analogous to the one for the definition of the electric field, E equals FE divided by Q. The SI unit of magnetic field is the Tesla. Another commonly used non-SI unit for B is the Gauss. The relationship between Tesla and Gauss is shown here. The magnetic field is then defined in terms of the force acting on the moving charged particle. How to determine the direction of FB? Please look at the figure showing the right-hand rule for the cross product of V and B. Our forefingers point along the direction of V and curl them toward B. The extended thumb points in the direction of V cross B. Because FB is the cross product of V and B times Q, FB is in the direction of your thumb if Q is positive and is opposite the direction of your thumb if Q is negative. Next, let's compare the differences between the electric force and the magnetic force of the particle in a field model. First, the electric force vector is along the direction of the electric field, whereas the magnetic force vector is perpendicular to the magnetic field. Second, the electric force acts on the charged particle regardless of whether the particle is moving or not, while the magnetic force acts on the charged particle only when the particle is in motion. Third, the electric force does work on the charged particle by moving it in a field, whereas the magnetic force associated with a steady magnetic field does no work on the charged particle because FB is always perpendicular to the velocity. Therefore, the direction of V can be changed by FB, but not the speed or the kinetic energy. Now please consider a charged particle moving in a magnetic field. How about its motion? We are discussing it next lecture.